Deep beneath the English Channel, one of the most ambitious engineering projects ever attempted was about to begin. Using earth-eating robotic monsters, 13,000 workers were about to embark upon an epic quest to build the longest undersea railway tunnel in the world. This historic journey would push the limits of technology and human determination to the breaking point. Some workers would not survive. The creation of the Eurotunnel is a story of engineering triumph and would be known as one of this century's greatest superstructures. Ever since the Ice Age ripped them apart 10,000 years ago, a small finger of ocean, the English Channel, has been the only path between England and Europe. For centuries, amateur designers and skilled engineers alike have tried and failed to create a safe, permanent link.
The first channel tunnel design, if you can call it a design, was in 1802. But at that time, the technology was so limited that really it was science fiction.
But by the end of the 20th century, the line separating technology and science fiction is rapidly disappearing. It's now possible to create machines the size of large buildings, machines that can literally move mountains. Inside factories like these, engineers began experimenting with space-age technologies which would take humans into new and potentially dangerous territories. An age-old question was being asked once more. Could a tunnel be created under the English Channel? The question itself raised heated debates. For centuries, the channel had served as natural protector against enemies both violently and ideologically opposed to the sovereign state. Would-be conquerors from Napoleon to Hitler developed plans of how they could first defeat the English Channel and then England itself. Ironically, during World War II, Adolf Hitler developed a plan to dig a tunnel near the captured French town of Calais, site of the modern-day French Eurotunnel station. It was a threat the Allied forces took seriously.
Bomber pilots were requested to report any plumes of grey material in the channel, and they actually established soldiers along the coast here with listening devices, trying to detect any sounds of tunnelling.
But with the defeat of Germany in World War II, Europe entered a new era. The sounds of war were replaced by the sounds of commerce. By 1986, one-time rivals England and France realized that the Channel had become an economic barrier, an obstacle that must be eliminated. To achieve this, the French and British governments dedicated themselves to the task of building a modern marvel, the world's most technologically advanced undersea tunnel. Engineers and business people alike dreamt of high-speed rail trains traveling beneath the English Channel, carrying the citizens of a united Europe into newfound economic opportunity. But before the first shovel of dirt was even dug, the project seemed destined for failure.
This was a nightmare at the time. We had to decide on things which we didn't really know about. And one example which I always quote is, what diameter do you want for the tunnel? Now you would think that this was something that had been decided before, but it hadn't. And the contractors kept pestering us, saying, what size tunnel do you want? And we said, well, listen, we just arrived. I don't know.
But the initial problems were not just technical. There was much public opposition to the project, especially on the British side. Some opponents were concerned about the environmental impact of the project, while others didn't want to surrender England's status as an island nation. The project's decision-making body, a consortium of 10 privately funded companies called Transmanche Limited, were undaunted. They planned a design of 3 parallel tube-like tunnels. When finished, these massive tunnels would form a railway loop between England and France. Engineers envisaged a system that would carry thousands of passengers and hundreds of tons of freight each day on the circular 30-minute trip. Of the 56 kilometres between the French terminal at Calais and the British terminal at Folkestone, 38 kilometres would be undersea. No other project had ever attempted to tunnel this far in such a hostile environment.
There are lots of problems, technical problems. How will a car move inside the tunnel? What kind of trucks can I transport? You know, all the variety of things.
As the project began in late 1986, all of these questions remained. But before issues regarding the tunnel's operation can be addressed, the most daunting and obvious problem would have to be solved. A machine that could chew through more than 50 kilometres of solid rock 100 metres below the sea didn't exist. It would have to be created. Far from the English Channel, on the outskirts of Seattle, Washington, a solution was being forged from iron and steel. Here, at the Robbins Company, a firm specializing in heavy mining and tunneling equipment, the next breed of super machines was being created. In this colossal factory was a mechanical beast that dwarfed its creators, a tunnel boring machine, or TBM. When finished, this giant snake-like machine would be over 250 meters long and weigh over 1,500 tons. Its rotating head would be over 15 meters in diameter, incorporating hundreds of cutting edges made from tungsten carbide, one of the hardest materials known to man. These would be the teeth of this mechanical monster, the cutting edge which would pave the way for the engineers. To push the machine forward, a series of powerful hydraulic devices called rams were devised to drive the cutting head through the rock. The millions of tons of excavated rock called spoil would be carried out on conveyor belts through the TBM's service train attached to the cutting head. The challenge of carving tunnels through solid rock has pushed the boundaries of engineering and manufacturing skill. Even today, it requires a rare balance of brain and brawn. When large-scale projects like the Los Angeles aqueduct system were being created in the 1930s, tunneling technology was in its infancy. Today, the Robbins Company will replace blasts of dynamite with a computerized mechanical marvel of which the early pioneers could only imagine. But the danger these modern miners face will also be unparalleled. At its deepest point, the tunnel would be 75 meters below the seabed. During construction, if their boring efforts created a crack in the tunnel or caused a leak, the force of the incoming water would be equivalent to over 7,000 tons of falling weight. While the route of the tunnel involved relatively simple excavation on the English side, the situation on the French side was far more treacherous. Here, the seabed is riddled with faults and fissures, conditions that are hazardous at the best of times. Of the 11 TBMs that would be created for this mission, the machines used on the French side would have the most difficult job. Working at greater depths, in parts of the seabed that are far less stable than the British side, these undersea giants would have to withstand pressures twice as intense as any tunneling machines ever experienced before. So engineers decided to create a special TBM that was part boring machine, part submarine. When finished, it would be able to withstand the same amount of undersea pressure as a World War II submarine. By December 1987, the race to complete the project on time and on budget began here, at 2 huge shafts at Sangatte, France, and Shakespeare Cliff in England. too enormous to be delivered to the site as complete machines, the first TBMs were lowered piece by piece into the darkness of the shafts. Going with them were the workers, the men behind the machines. They too were descending into the unknown. As the first work began and the light of day slowly disappeared, there was an air of hope, expectation, and much uncertainty. While extraordinary safety measures had been taken to protect the workers, it remained a dangerous world. And for some, the greatest civil engineering project of the 20th century would carry the ultimate price. As the building work began, the surrounding areas of the proposed terminals started to take shape. Massive scars in the earth marked the spot where the trains would enter the tunnels. But compounding the awesome challenge of the actual tunneling operation was the human challenge itself. British and French workers, once bitter rivals, had to work closely together. Once they reached dangerous caverns deep below the earth, there could be no room for cultural misunderstandings.
A French engineer is trained to make a plan. They can't start work unless they can see what there is to be done, see where their task fits into the whole thing, and see how it's all going to be organized as it goes along. No such thing in the British culture. British culture is to sit down and say, now what have we got to do, chaps? And sort out who's going to do what and set to work.
One of the first problems they faced was the assembly of the giant tunnel boring machines. Even the smallest machine took months to build and cost several $millions. The largest of these subterranean titans weighed 1,500 tons. Because of their enormous size and weight, the TBMs would have to be assembled on site at the bottom of the shafts. The actual cutting head of the TBM is just the tip of its immense body. Attached to it is the service train, a multi-car train system that carries the hydraulic power to drive the TBMs forward. When connected to the cutting head, each service train is a staggering 260 meters. One of the service train's main functions was to be a conduit for the removal of millions of tons of rock and sediment that these mechanical moles would dig up. The debris was then carried by conveyor belt through the service train to a separate supply train further back, and final dispersal in England and France. The removal of the spoil was a major challenge. When operating at full speed, engineers estimated the TBMs would cut through 250 meters of rock a day, removing 2,400 tons of waste per hour. When the project was finished, the total amount of rock removed would fill a major football stadium 13 times. But that was nothing compared to the job of getting the building materials into the tunnel itself. At the sites for the Channel Tunnel, there was a build-up of materials not seen since the preparations for D-Day. And one of the most crucial building blocks were the 500,000 concrete slabs which would line the tunnel walls. Each ring is made of specially reinforced concrete, a material stronger than the concrete used in nuclear power plants. It's also reinforced with a framework of steel rods for extra resistance. This was necessary because the savage ocean pressure which would bear down on the tunnel walls is equivalent to 12 atmospheres. No human could survive under such immense force. Once the rings were finished, they were transported by narrow-gauge railway to the TBMs in the tunnel and brought up through the service train. Then a remarkable display of mechanical symmetry took place. As the spinning head of the machine clawed its way through the rock, operators using giant cranes created the tunnel walls right behind them. After being fitted into place with incredible precision, a gap of only 2 centimeters remained between each section. This tiny space was then sealed with a cement grout, and another piece of the tunnel wall was completed. When finished, each ring of the tunnel would weigh 40 tons. But just as the skeleton of the tunnel was beginning to take shape, the project itself suddenly seemed in danger of falling apart. It was now 1988. The British and French teams were starting with the middle service tunnel, drilling towards each other and meeting in the middle of the channel. But by May, the giant tunneling machines started to break down.
It was designed to operate at pressures that no machine had ever operated before. It was strictly a prototype as a result of the fact that it was so complex and nothing like it had ever been built. It had all kinds of troubles. Practically everything important on the machine failed or broke at one time or another shortly after we installed the machine.
On the French side, the TBMs were encountering precisely what the engineers feared most: hidden faults and fissures in the seabed. On the other side of these cracks lay the awesome force of the English Channel.
It was technically very difficult because the water pressure that we had to work in, as the machine bored forward, it bored right through faults that were filled with seawater, connected directly to the ocean.
Waterproofing measures designed to protect the TBM's delicate electronic equipment from the corrosive seawater failed, stopping the giant machines in their tracks. Then, as engineers scrambled to repair the electrical problem, another even larger problem developed. The ring of watertight seals providing a life-saving barrier between the TBMs and the tunnel walls also began to fail, again victims of saltwater corrosion. Engineers needed a solution if the project was to succeed. The corroded brush-like lining seals were replaced. Then a mixture of paper and special grease was applied to the brushes. When this coating came into contact with seawater, the paper particles expanded and created a permanent watertight bond between the segments. The TBM was once again waterproof. But to Richard Robbins, the tunnel walls seemed far more secure than the legal agreement he was working under. Soon, he was forced into a desperate personal gamble.
The French contractor knew that we had designed a prototype machine that we didn't really understand exactly what it was going to cost us to build. So he built into the job some interesting incentives that if we met certain project construction points along the tunnel by certain dates, we would earn bonuses. But it was so bad in the early stages that I was really almost betting the entire company that we would succeed. So it was a big risk for a small company like ours.
But it wasn't just contractors like the Robbins Company who were gambling their future. Because the entire project was privately funded, Eurotunnel officials were vulnerable to the demands of their shareholders, and more importantly, the banks. With each new delay, the entire fate of the Eurotunnel lay in the balance.
The one thing we all understood was that if we stopped, it would be very hard to restart. The relationship with the banks, the problems with the contractors, the difficulties with the governments, or just plain organizational difficulties of whatever kind, would very probably bring an end to the project.
Finally, engineers were able to redesign the mechanical flaws in the French TBM and move ahead. But they were now 9 months behind schedule. Both the British and French teams could not allow another delay such as this. One of the greatest problems the engineers had to solve now was how to ensure the TBMs, tunneling towards each other from opposite directions, would stay on course. They were far too deep below the Earth for high-tech satellite mapping to be of any use, and even the slightest fraction of any deviation would mean that they would fail to meet in the middle. To remain on track, tunnel engineers used a laser beam guidance system. Here, a laser emits a beam from behind the cutting head. As it sends a beam of light forward, it hits various control points fixed to the tunnel wall, before striking a special target on the rear of the cutting head. These control points feed information provided from the laser straight into the machine's onboard computer. From the TBM control cabin, operators could now adjust the hydraulic rams which thrust the TBM forward and keep it on exactly the right course. But even if the two machines did stay on course, the complex plan for after they met had never been tried before. As the French and British TBMs tunneled towards each other, they would reach a designated point where they stopped. They would now be a mere 90 meters apart. At that point, a long steel probe would be sent through to determine if they'd truly been on course. If so, more conventional equipment would finish the relatively short distance that remained. But if the two machines were off course, it would mean yet another delay. With the project's skyrocketing budget increasingly under fire, more delays could signal the end of the dream called Eurotunnel. (1989). The year began on an uneven note at the Eurotunnel construction sites. The earlier problems with the French tunnel boring machines seemed to be solved. One of the giant TBMs had even set a world tunneling record of 1,000 meters in 1 month. For almost 3 years, work on the tunnel had progressed without a fatality. But in the first days of the new year, a time usually associated with hope and new beginnings, a tragedy lay just around the corner. On January the 20th, in the dark recesses of this massive cavern, the tunnel claimed its first victim. 19-year-old engineer's assistant Andrew McKenna was walking a kilometre down the tunnel beside the narrow-gauge railway tracks used by the supply carts. Apparently failing to hear an oncoming train, he was crushed to death by a mini locomotive carrying spoil from the site. Without warning, the stark reality of their dangerous jobs became clear to every worker. The tunnel had claimed one of their own. Even with 20th century technology, the job of building tunnels remains extremely hazardous. While the workers coped with their loss, they also had to deal with the other day-to-day fears brought on by the tunnel.
At the pumping stations, they actually went underneath the tunnels, and there would be like a little tunnel under the main tunnels, so the trains would be going above you, and you could be down working in 3 foot of water in a little cross passage with a blank wall with nowhere else to go, and that could be very claustrophobic. And we actually experienced people being sent in to work with us who were and found out they're claustrophobic. And then it became a little bit scary because you had to say to them, look, you can't work with us down here, you're terrified of the situation, and you had to think of everybody else's safety. It was dark, it could be dusty, so you had to be able to cope and have a sort of positive outlook, really.
As workers got on with the tasks below ground, above them, work continued on the high-tech trains that would use the system when completed. The new service being created exclusively for the Eurotunnel is christened Le Shuttle. When finished, Le Shuttle trains would carry passengers and their cars on a continuous loop between the terminals in England and Calais. In plants like these, workers used more than 10,000 welds to mould more than 5,000 parts into the single shell of a train car. Each Le Shuttle train was being specially built for the frequent trips and heavy loads it would haul. To provide maximum power, a 132-ton locomotive is placed at each end of the train.
They have to be very special trains because the trains themselves are half a mile long, and they have a lot of cars inside them or a lot of trucks, and therefore the locomotives have to be very powerful. They're the most powerful locomotives in the world.
Each of these must be capable of pulling a 2,400-ton train by itself. For this kind of power, they need 25,000 volts of electricity. This high-voltage energy, carried in the cables, provides the equivalent force of a 7,600 horsepower engine, about 100 times the power of an average car. But while the shuttle trains may have the most powerful locomotives on Earth, the sleek, high-speed Eurostar trains have the world's fastest. The Eurostar passenger line uses the popular TGV trains, which travel from Paris to London at speeds of 300 kilometers per hour. But while in the tunnel, the trains are only allowed to travel at more modest speeds, approaching 160. Because the transport of commercial freight is so vital to Eurotunnel's economic future, huge new rail cars were designed to transport articulated lorries. Each freight shuttle consists of 28 carrier wagons, and each carrier wagon can accommodate a truck weighing up to 44 tons. Autumn 1990. Deep below the Earth, the mood of expectancy was tangible. After 3 years of tunnelling, the British and French TBMs digging the service tunnel, which would run between the two rail tunnels, had arrived at their undersea destination. Facing each other under the English Channel, 90 meters apart, the machines had stopped their digging. It was eerily quiet, and the same question raced through each worker's mind. Had they lined up? A probe was sent through. Each worker at every level of the project knew it would be a catastrophe if the tunnels were a mere fraction off course. This would be the type of mistake that could send the entire project into free fall. Finally, they got the news. The tunnels are lined up. England, by virtue of a 90-meter pole, was no longer an island. After boring through over 35 kilometers of solid rock for 3 long years, the tunnels were only off by 50 centimeters, well within the acceptable safety margin. It was a momentous achievement. While the project's workers, a unique collection of specialists from across the globe, revelled in their victory, a celebration was quickly planned for the face-to-face breakthrough. As there was still a 90-meter gap between England and France to address, it was decided that the official breakthrough on the service tunnel would take place on December the 1st. As workers returned to their jobs with a new sense of accomplishment, a lottery was held to pick one worker from each country to meet in the completed tunnel. Meanwhile, there was the problem of what to do about the last 90 meters. As it was too expensive to retrieve both the French and the British machines, a unique solution was developed. The British aimed their machine downwards and effectively committed mechanical suicide, burying the high-tech behemoth deep into the earth. This allowed the French TBM to move forward and connect with the British side of the tunnel. December the 1st, 1990. Finally the moment of truth. A thin layer of chalk was all that lay between Britain and France and separated Frenchman Philippe Cosette and Englishman Graham Fagg. With a couple of well-directed jackhammer blasts, a barrier that had stood for 10,000 years was demolished. One of the most ambitious engineering efforts of the 20th century climaxed with a simple gesture of goodwill. Beneath the English Channel, a Frenchman and an Englishman met through a small hole. For the first time since glaciers ripped them apart thousands of years ago, France and England were once again linked.
Vive la France! Yeah. Come! The atmosphere was absolutely electric down there, not only just at the breakthrough but afterwards, and people were moving. We all felt European. I don't think anybody felt English or French. We were all European at the instant, and for the brief hour before we could actually set off back to our respective sides. Amazing scene, really wouldn't have missed it for anything.
The next few months would hold many more extraordinary moments. The public got an opportunity to share with history the above-ground breakthroughs, firstly in France, and then in England.
When that tunnel broke through, there was a party that would end all parties. It practically went all night. It was at the Windsor Castle on the British side. Fireworks and feasting and about 1,000 guests, and it was really a marvelous party.
What I remember is sitting down there, having the feeling there is no more machinery running now, and a feeling in amongst the most tremendous uproar, popping champagne corks and backslapping and cheering and so on, a feeling of absolute silence. It was the most extraordinary feeling.
But amidst the revelry and the silence, the realization began to sink in that there was still a long way to go. 2 more tunnels needed to be created, not to mention the installation of the high-speed railway. Work on the Eurotunnel was far from over. As the parties celebrating the breakthrough of Eurotunnel's service tunnel faded away, efforts to complete the 2 remaining railway tunnels resumed at a pace. The 2 main rail tunnels are called running tunnels. To allow trains to switch from one track to another, massive crossover caverns are carved from the seabed. 13 meters high and over 150 meters long, they're the largest undersea structures ever created. Workers refer to these caverns as cathedrals, but in the event of a deadly fire, they could quickly become a scene of mass terror. So to prevent fire from spreading from one running tunnel to the other, engineers created giant doors to separate them. Each door is made from super strong carbon manganese steel. Then a layer of flame-resistant material was added. These fireproof walls are a movable fortress, weighing over 100 tons each. But fire isn't the only emergency tunnel officials must prepare for. Terrorist attacks, bomb threats, and even the remote possibility of an earthquake are all scenarios which must be planned for.
The evacuation train will be with us in approximately 6 minutes' time.
A specially trained security force and evacuation team was established, which constantly rehearsed emergency procedures. While they speak the same language in times of emergency, French and British officials still had different beliefs regarding issues of safety.
There are 2 different safety philosophies. The French have a belief in intelligent operators using sophisticated equipment, but in charge of the equipment. The British have a culture of fail-safe computers. Channel Tunnel, you've got an aggregation of both, so you can be quite sure whichever you think is better, the tunnel's got it.
No other tunnel in the world is as safe as this one, with the central service tunnel, the fire supply systems, duplication of power supplies, emergency walkways, and all the procedures that have been put in place to cover every eventuality.
But there was one eventuality engineers hadn't planned for. As they performed test runs in the tunnels, the friction of the trains moving through them was producing an enormous amount of heat, raising temperatures to a sizzling 60 degrees Celsius. Scrambling for a solution, engineers created a pipeline filled with chilled flowing water to keep the heat in the tunnel from accumulating. This cold water acts like a sponge to absorb the tunnel's heat. The water, now warmed, is pumped to a cooling station on shore, re-chilled, and then recirculated. Elsewhere, the two rail terminals that would serve as Eurotunnel's passenger hubs are starting to take shape. The massive French terminal at Calais is one of the largest construction projects in the world. Within its sprawling 18-kilometre perimeter, the Calais station will have 50 kilometres of roadway and rail track. While the British terminal at Folkestone is small in comparison, 5 times smaller than the French one, it houses the nerve centre of the entire Eurotunnel system. Here, in the Folkestone Command Centre, operators use state-of-the-art technology to control all of the rail traffic that moves through the tunnel. Sitting behind 3 rows of desks, they can survey a curved wall showing the status of the entire system. This high-tech display is called a mimic board. It shows the position of every train in the tunnel and at the terminals. In the event of a power failure, tunnel control immediately switches over to the Calais control centre, which is staffed at all times in case of emergency. Even the drivers of the shuttle trains receive high-tech assistance. In this driving simulator, operators practice navigating through the tunnel. In real life, the driver of each shuttle sits in the front locomotive, while the captain of the train sits in the rear. The captain, who's ultimately responsible for the safety of the passengers, communicates with the driver by intercom. But the onboard computers also have command status. If the train begins to move too fast, the shuttle's brakes will go on automatically. By the middle of 1991, the project's infrastructure was beginning to take form. From the terminals to the trains themselves, it seemed that the dream of an undersea rail link would soon be realized. But deep underground, 2 more hurdles remained: the completion of the northern and southern rail tunnels. On May the 22nd, the first of those obstacles disappeared into history as the northern running tunnel was completed. This is the tunnel that will carry passengers from Britain to France. But on this day, it's a symbol of a united Europe. Just over a month later, on June the 28th, 1991, huge crowds gathered for the completion of the southern tunnel. The last TBM punched through the last remaining wall and came to a stop. 4 years after digging had begun, one of the most difficult engineering challenges of history was now complete. While workers celebrated and drank champagne, the machines finally fell silent. It was a defining moment in the long history of these once warring nations. A line had been crossed which could never be redrawn. For better or worse, 2 proud countries had formed an irrevocable link.
What is being created here and what has been achieved to date is of enormous value for the future of both our countries and of Europe. Thank you.
In all, over 13,000 workers had worked for more than 6 years. Besides the 3 main undersea tunnels, each over 50 kilometres long, 9 other smaller access tunnels were also created. The amount of material removed on the British side increased England's landmass by over 30 hectares. Engineering officials believed the hard part was over. In fact, contractors like Richard Robbins collected bonuses for finishing ahead of schedule. But the harsh winds of reality brought a sobering truth of a bloated budget and an uncertain future. To Eurotunnel officials, the hard part had just begun. The powerful locomotives that were to pull the 1 kilometre-long train 20 times a day were delivered to the terminal at Calais in France. Finally, on May the 6th, 1994, the grand experiment was about to begin. After boarding one of the luxury Eurostar trains in London, Her Majesty Queen Elizabeth II arrived via the tunnel in Calais. This would be just the first part of an all-day celebration scheduled in both countries. Her Majesty was received by the French President François Mitterrand. After a ribbon-cutting ceremony, the Queen and the French President departed in Her Majesty's Rolls-Royce to travel on Le Shuttle back to England. The image was a powerful one, as Eurotunnel's ceremonial first passengers symbolized the first new Europeans, able to cross a once formidable barrier with grace and ease. Arriving back in England for the second phase of the ceremony, Her Majesty took time to greet each crew member honoured with making this historic inaugural journey. But as the ceremonies and media attention faded away, so did the public's interest. Initial usage of the tunnel was far below expectations. Critics of the Eurotunnel's cost, now almost $21 billion, were again on the warpath. Then, less than 2 years later, evening broadcasts spread the news officials feared most. An accident had occurred in the tunnel. On November the 18th, 1996, fire ripped through a freight train bound for England. Trapped in smothering fumes for nearly half an hour, passengers ignored requests to wait for help and abandoned the train, groping their way to safety in the service tunnel. The fire was so hot it transformed the cargo of mammoth trucks into unrecognizable lumps of melted steel. 8 of the 34 crew members of the freight train suffered smoke inhalation, and the tunnel was badly damaged. What has been called the safest tunnel in the world was now brought to its knees. Amid a firestorm of public controversy, the Eurotunnel was closed. 460 meters of railway track and 50 meters of the tunnel's reinforced concrete lining were wrecked and needed to be replaced. The damage caused by this accident, estimated at almost $100 million, made it one of the costliest rail accidents in history. While no one was seriously injured, public confidence in the tunnel plummeted. Eurotunnel officials went on the defensive.
12 hours later, nobody was in hospital. Yet there'd been a 1,500 degrees centigrade fire 300 feet away from them. Nobody was in hospital. Now say that about a highway crash, or about a ferry sinking, or about a plane crash. You can't.
17 days later, Eurotunnel officials staged an emergency evacuation drill designed to reassure the public that the tunnel was safe. A drill criticized for being more a public relations exercise than a safety one. Despite the disaster, the tunnel reopened to passenger traffic several weeks later. But the badly burned Southern Rail Tunnel was closed for 6 months while the damaged tracks were repaired. Finally, commercial freight traffic resumed on June the 15th, almost 7 months after the accident. As this disaster faded from the headlines, so did the fears in the general public. But what hasn't gone away is the sacrifice made by over 13,000 men and women who created this architectural marvel. This plaque at England's Shakespeare Cliff pays tribute to the 12 workers who lost their lives working to create the Eurotunnel. Theirs was the ultimate sacrifice. The job of being a tunneler, of staring at a mountain or ocean and seeing a way to cross it, has always required a special skill. A person who can exist without natural light, in suffocating holes, working for long periods of time towards a seemingly impossible goal.
Tunnellers are a special breed of people. They move around the world building holes in the ground. And most of their work is never seen by anybody else, but they do take a pride in building a good tunnel.
It remains to be seen whether or not Eurotunnel and the infrastructure surrounding it will be a financial success. But officials claim immediate financial return was never the sole concern.
The philosophy of the investors was not, curiously, mostly financial. They said it doesn't matter whether we don't see any return. We think the benefits for our children, our grandchildren, are going to be extremely important.
The Folkestone terminal in England and the Calais terminal in France are now ports of call to thousands of travellers. This undersea journey, for centuries the subject of scorn and ridicule, now seems routine, the shortest distance between 2 points.
If you were British and you lived here, we're an island, and if you want to get off this island, in the past the only way is either to get on a boat or to fly. And for the first time ever now, you can take a train. You don't have to change, you don't have to get off. You get on the train in central London, and you get off, and you're suddenly in central Paris, and it's a whole new culture.
Whatever brings these travellers to England or France, the size of the world they lived in before is now smaller because of the Channel. A physical barrier that has stood for 10,000 years has disappeared. Europe is already more united.
Whatever the political structures, whatever the legislative structures, the economic and social coming together is unstoppable. And it's happening, and the tunnel plays a key part in that, and is symbolic of it.
The Eurotunnel remains one of the greatest engineering achievements of this century. For the thousands of men and women who built this tunnel, it stands as a monument to their belief that the impossible is simply a challenge, a temporary obstacle that can be overcome with technology, skill, and perseverance.
Having lived with it for the last 10, 12 years, I feel something special about it every time I come in. I'm quite amazed by the amount of work that went into the tunnel, the complexity of all the equipment, and the short time that it took to build this modern wonder of the world.
In the end, the Channel may be viewed as more of a bridge than a tunnel. As these high-tech trains speed beneath the ocean, they carry with them an uncertain future as borders are crossed in the blink of an eye and old ideals crumble in the face of new technologies.